to this. Okay, so I am especially pleased to introduce Dr. Linda McIver, who is, she may not know this, but her scholarship inspired me considerably, especially when I was a graduate student. I read her dissertation, I can't tell you how many times, on a lot of the early work that she did at the time. She did some really cool work on really thinking about evidence related to programming languages long before it was cool, long before it was cool, which is what inspired me a great deal. She is now the executive director of the Australian Data Science Education Institute, which I know basically nothing about, but when I had heard that she was doing that, I thought that none of us probably had any idea what they were doing in Australia related to data science. So I'm extremely pleased that Linda was able to come talk to us today. I hope all of you are interested in the kind of work that she's doing. And for Linda, we're all trying to make data science accessible so that if you can do data science, but also if you're blind or deaf or have mobility impairments or any other number of things, we're trying to make sure that all those people can participate too. So that's what we're doing this year. And so I'm gonna untalk myself, and I will let you take it away. So
thanks so much, Stefik. That was a great introduction. And I should add that please don't take what I'm doing as the norm in Australia. Part of the reason I do what I do is that until recently there was very little data science education in schools in Australia, and you know, it's a work in progress. My goal is to put myself out of business because it'll just be the way things are done and the way teachers are taught, and it'll all be happening. But I don't think my job is in any immediate danger. So just to kick off, in Australia, we have a tradition of acknowledging the traditional owners of the land on which we stand. And unusually for me, I'm in Perth in Western Australia at the moment. Normally I'm in Melbourne and in Victoria, but that means that I am on the lands of the Whadjuk people of the Noongar Nation. And that's because Pawsey Supercomputing Centre is hosting me, giving me the use of their facilities to do this talk. So I'm very grateful to them. They've been very good to me. I'm also I'd like to thank Stefik and the organizers for inviting me. This is very exciting and has given me the kick to look for more projects that are relevant for the visually impaired and that can be more useful for your community. So that's been really awesome as well. And I'd also like to thank Stefik for reading my PhD thesis apparently more than once, because they're often considered write-only documents. The idea that someone reads one is quite revolutionary. I noted that.
I liked your dissertation a lot, which is why I read it. It made me really think.
That's awesome. It's really good to know.
Sorry, I don't mean to interrupt. I was just going to say, what in your actual academic papers on your dissertation, there was so much detail that you didn't get if you didn't read the actual document. That's why I went back to the original source so many times. Anyway, sorry, I'll stop talking. But
sure you will. Look, no, I'm quite pleased for the introduction. Please feel free to pitch in. I will try to keep an eye on the chat, but once I get talking, I get a little bit tunnel visioned. So if you would like to unmute yourself and pitch in a question or a comment, please feel free. It's wonderful to have it more interactive. I know that the title is a little bit confronting, possibly more confronting in the US than it is here. The term heresy it can be a really uncomfortable one. It has a long and uncomfortable history. And I was actually wondering whether I should change it for a US audience, but I came to the conclusion that discomfort is actually a prerequisite for change and for progress. So I'm going to tell you some stories about heresy in science and in the wider world, and also some stories about the tech industry. And we're going to laugh and mock the tech industry, and rightly so. But there's also going to be some stories about the education system, which might also make those of us who are educators, which I think is everybody here, quite uncomfortable. So that's the goal is to use that discomfort well. So that we can use it to create change and to create progress and to encourage our kids to be change makers and critical thinkers and problem solvers, because I think the world needs quite a lot of that at the moment in particular. So Stefik, I believe, has put the link to the slides in the Slack. So please feel free to follow along. I'm not going to share my screen because I want to be able to see you and for you to see me and have it more, you know, a little more interactive if possible. So if you feel comfortable putting your camera on, please do so. If not, that's perfectly fine. But as I say, please feel free to interact along the way as well. Whoops. Okay. So as I said, we're going to talk a little bit about the technology industry. But before we get into that, I want to start talking about the place of heresy in science, because this is really where the idea of heretics came from. And some of these stories will be really familiar to you if you think about, you know, Galileo it was sort of one of our best known and earliest heretics, and he was, you know, literally accused of heresy and put under house arrest, narrowly escaping death for daring to suggest that the world was round and that the Earth went around. That the Earth went around the sun. It's early and I haven't had enough coffee. But one of the more recent and kind of impactful heresies is from a scientist by the name of Lindsay Marr. Has anyone heard of Lindsay? She is my hero at the moment because in 2011, she proved that the flu is airborne and not droplet spread, which means that, so until then, the scientific and medical orthodoxy was that you caught the flu by being in the direct path of droplets. So someone coughs or sneezes, you get droplets, or you pick up droplets from surfaces or whatever, and that's how you catch the flu. You touch your face, and you know, we've probably all heard that story. What she did, because she's an aerosol engineer as well as a health researcher, she actually measured the air up in the top of a room around the air intakes, you know, the air distribution system, and she found enough flu in that air, just suspended in that air, to make people sick, which is significant because droplets fly, but then they fall and they don't stay in the air. So if you walk into a room 5 minutes after someone with the flu has been there and it's only droplet spread, you're not going to get sick unless you touch a surface and then touch your face. But if it's airborne, that can stay for hours. And she proved this in 2011, that it's airborne. And she was told that was ridiculous because the scientific orthodoxy was that particles larger than 5 microns could not remain airborne and therefore could not make you sick. She knew that it could. She had the evidence in front of her, but she couldn't get published. She eventually got published in a tiny little niche journal and it did not hit the mainstream. Now, that's bad for the flu, but the implications of that for us for the last few years are really significant because the same orthodoxy was applied to the understanding of COVID. And the medical orthodoxy, you may recall, was you need to socially distance because then the droplets will only fly so far, and social distancing and hand sanitization are what we need to keep us safe. But because COVID is airborne, not droplet spread, that's not true. What we need is better filtration, and we need masks, and we need better ventilation. And it took 18 months to get to the point of believing that. And Lindsay was at the forefront of that kind of fight to get the World Health Organization and authorities all around the world to understand that COVID is airborne, not droplet spread. And so she teamed up with a research archaeologist, which is a term that I had never heard before, which is basically someone who digs through historical research and literature to try to find the origins of the idea. And the idea that 5 microns was the largest particle that could be airborne was traced back eventually, after much trauma, to a 1930s study on tuberculosis, which found that particles larger than 5 microns cannot give you tuberculosis. The trouble is, the reason for that is that particles larger than 5 microns can't make it deep into the lungs, and the particles have to make it deep into the lungs in order to give you tuberculosis. They don't have to make it deep into the lungs to give you the flu or to give you COVID. So the bit that was remembered from that study was 5 microns, not the key bits around it. And that actually fixed medical orthodoxy for nearly 100 years, that misunderstanding of one study. And had Lindsay not been a heretic, she would not have even studied that. She would not have even looked to find the truth of that and to find that flu is in fact airborne rather than droplet spread, and that therefore COVID is too. She had to be heretical. She had to be prepared to say what everybody knows is right is not right. And that's a theme through a lot of our science, and it has a real impact. You know, if she had been able to get her, if the World Health Organization had paid closer attention to that earlier on, we would have had a lot less deaths from COVID, because people would have made you know, better choices that have been masking and that have been ventilation and all that kind of stuff. So pretty awesome. I've popped the name in the chat with what I think is the right spelling, but if you look for MAR and COVID and airborne, I'm sure you'll find her. If you don't, let me know. So that's kind of my topical favorite heresy story. There's also, you know, there's so many in history. We talked about Galileo for a moment there. There was Alfred Wegener, who proposed the theory that the continents, the continents are a thing and that they move. Tectonic plates are a thing. There's Barbara McClintock, who discovered that genes actually, that there are parts of the genetic material, the genetic code, that actually impact our bodies that are outside the actual coded genes that we know about. So basically the junk DNA is important. And she also was widely pilloried before her ideas became accepted, and that's now established science. And she again had to go against the scientific orthodoxy and say, I don't think what we all know is true is actually true. So it's a really important thing for the progress of science for that to happen. Alice C. Evans is a great story from the US. She discovered that pasteurization of milk kills a lot of milk-borne diseases. She struggled to get that published, partly because she was a woman and women weren't allowed to publish research at the time. They weren't allowed to get PhDs. And also because people thought it was just, you know, madness. And she actually contracted a very nasty milk-borne disease before that was called undulant fever, before the whole thing was established as science. And now, of course, most of us drink pasteurized milk and accept that it's a great way not to get things like tuberculosis and things like that. So heresy is really important. You've got to be prepared to stand up and go, I don't think that's right. And the key thing is, I'm going to prove it. So we don't want YouTube-based heresy. We want rational, evidence-based heresy, right? And that's a really important distinction to make at the moment in particular, given the conspiracy theories and other challenges that we're facing at the moment. So I want to move on from heresy to the story, which I'm sure some of you have heard, of World War II planes that were examined when they came back from battle. They were examined for bullet holes. And they found that the planes that came back, the bullet holes were mostly around the wings and the tail. And so they thought, okay, clearly these are the parts of the plane that we need to reinforce, and we need to put better armor on. All the parts of the plane that came back with bullet holes, those are the ones we need to make stronger. Until a statistician actually said, hang on a minute, the planes that get bullet holes in other places are the ones that don't make it back. So actually, that's the fuselage and the engines and the fuel tanks. Those are the parts that are when we hit them, we lose those planes. So that's a classic case of what we call survivorship bias, where you measure based on the ones that made it back or the ones that you have, and you don't actually think about why you don't have the other evidence. There was a similar story from World War I, which was that when they introduced helmets, they were suddenly started treating a lot more head injuries in field hospitals. And they were like, helmets cause head injuries. We need to stop using helmets. Until someone pointed out, no, the people are actually surviving the head injuries now, which is why we're treating them. So the way you interpret the data is really important. I've got some stories about that later on as well. But this is where I start giving the tech industry a hard time. because one of the classic stories, or it's becoming classic, about the tech industry not understanding data is a company by the name of HireVue, which is a human resources tech company that uses artificial intelligence to interview and select recruits for your company. And they select or reject candidates based on we don't know, because it's artificial intelligence. It's a black box. And partly they don't want to tell us as well because it's commercial in confidence. So they say it's a machine and therefore it's without bias. Pause for hysterical laughter. But we can mock that, but over 100 companies are already using it, including big ones like Hilton and Unilever. So it's very, very popular. And it's all kinds of disturbing because they can't explain how it makes its decisions. And so they say it's without bias, but they have no evidence to back that up. They say it employs superhuman precision and impartiality to zero in on an ideal employee, picking up on telltale clues a recruiter might miss. But they can't tell us how. And one of the big issues is that HireVue's algorithm was trained on previous hiring decisions. And this is a problem that we see in AI all the time, which is that it takes existing bias and codifies it and calls it unbiased. So now we have codified and possibly even magnified the bias, and we're doing a lot more decisions based on that bias. So the bias is being amplified, and now we're saying it's without bias because it's a machine decision. And there's a researcher who used to be at Microsoft who studies emotion and AI by the name of Luke Stark, and he describes this as the charisma of numbers. If an algorithm assigns a number to a person, then we think that's objective. We think that's incontrovertible and perfectly objective and without bias. And what could possibly go wrong reducing a complex and multifaceted human being to a numerical rank, something like the SATs, for example. Maybe those simple numerical ranks actually miss something. And I think Kathy O'Neill sums it up really well. She says, models are opinions embedded in mathematics, algorithms are opinions formalized in code. But we have this blind spot where computers are concerned and we think that they're objective and that they're unbiased and they're statements of truth. So it's really important that we remember that they're not. This, of course, is a textbook example of survivorship bias, because they're training the system on the people who made it through the previous recruitment system. They're not looking at the people who didn't make it through, who might have been incredible, might have been perfect, might have been, people who thought outside the box and actually made phenomenal changes. They're ignoring those entirely. It also highlights an issue I've seen raised again and again in books like Weapons of Math Destruction, which is Kathy O'Neill, Made by Humans by Ellen Broad, and Automating Inequality by Virginia Eubanks. I'll pop those in the chat later if someone hasn't before, because people believe in numbers and computers and algorithms over people, even when they've been explicitly told those systems are broken. And my favorite story about that is a friend of mine by the name of Niels Wouters, who was a researcher at Melbourne University, and he designed a system called Biometric Mirror. And it was a deliberately simple, absolutely naive machine learning system that was designed it would take a photo of you and then it would tell you stuff about yourself. It would tell you your ethnicity, your age, your gender, your attractiveness, your trustworthiness, that all of these attributes that it said it could work out just from looking at your face. And the goal of the whole system was to have the conversation about how obviously ludicrous it is to think that a computer system can do that. We can't do that. I can't look at you and tell your sexuality or your gender. I love that some of you have your pronouns in your Zoom names because I wouldn't know them otherwise. So it's insane to think that a computer system could do that. And that was the whole point of Biometric Mirror. So he set up booths where people would come, have a photo taken, read all of this obviously ludicrous information about themselves, and then have a conversation about trust and ethics and the issues with artificial intelligence. It was a noble goal, it was a great idea, but there are two postscripts to the story that really tell you more about humankind than you'd probably like to know. Which is that, first of all, having had the whole conversation about how ridiculous it was, he would hear people walking away sadly saying, but it's a computer, it must be right, and it doesn't think I'm attractive. So we had to take those real value judgments out because it was distressing people. But the worst part, the absolute worst part, is that after that, he was contacted after talking about how ludicrous it was, giving big talks about the whole idea of the system. He was repeatedly contacted by human resources companies wanting to buy biometric mirror. Yeah, I wish I had a photo of your face, Stefik, because that like it just. Did you even hear the talk? You know what? It's horrific, but that's I think that's a really good indication of our attitude to computers, even when we have someone standing there saying, this is wrong, this is flawed, this is broken, we have people who just want to use it and just want to believe in it. So this is where we start to make the connection between education and the tech industry. Because one of the problems with data science is that we often don't have a lot of time to think about challenging our own results, much less anybody else's. We have this tendency to go, we have data, we do some science, and then we have profit. And then we move on to the next thing. It's a rush and it's all very urgent and there is no time to sit down and ask those critical questions. Lindsay Ma was only able to prove that COVID was airborne by being skeptical, by challenging the status quo, by questioning accepted wisdom. We're not teaching our kids to do that. We're teaching our kids to get the right answer. We're teaching our kids to look up the answer at the back of the textbook and say, yep, I'm done, or to take the answer off the exam and go, yep, I got a ticker, I got 100%, and move on. We're not teaching them to go, how do I know that's right? What if it was wrong? What are the ways it might be wrong? So, of course, as I said before, we need educated heretics. We need rational skepticism, not denialism and wishful thinking. But that puts the onus back on education. And if you think about the way we teach STEM in particular, particularly sciences where we teach chemistry with here's an experiment where we give you 2 known reagents, we give you a known process to apply to them, and you are then expected to get a known output, right? So the kids who don't get the known output, what do? They either fake their results or they use the results of their neighbor, or they certainly don't sit down and go, why did I not get the expected results? Could it be that there was something wrong with the process? Could it be that I did something wrong? There's no time for that. You get marked on getting the right answer. You get marked on submitting the right graph and writing up the right process. This is not an education in science. This is an education in confirmation bias. And it's the absolute worst thing that we could be teaching our kids. And often tech education is even worse because we don't have enough teachers over here with programming skills. I imagine that's quite similar in the US. And so we tend to default to education using toys. We have people drawing pretty pictures in Scratch. We have them making robots follow lines and push each other out of circles. And the kids are writing the same code and producing the same output. Or if they're allowed to be creative, they're being creative in ways that aren't really very meaningful. They're just playing, and whatever the output is, that's the output. And they played, they did a pretty picture, done. So what if we could teach with experiments where we don't know the answers? And with data, the thing is we can really easily do that, because I could, can we find a data set that hasn't been fully analyzed and thoroughly understood? I could hit half a dozen with a bread roll from where I'm sitting. Like it's that they're everywhere. Making sense of them, that's another challenge and part of the reason I created my organization. But you don't have to have the kids getting the right answer. So what you mark instead of the right answer is you mark the process. You mark the testing. You ask the students to test and challenge their answers really thoroughly. And if they can't show that they've tested and challenged their answers, they don't get the marks. So you can come out with a result, but if you can't explain the process and you can't show how thoroughly you've tested it, and you can't tell me what's wrong with it, because there's always something wrong. If it's a real data set, there are problems. No such thing as a perfect data set except in a textbook. So you give points for their explanation of why they think that their answer is valid and for how they confirmed it by trying their hardest to prove that it's wrong. So you teach them that one of the most important skills is to be able to challenge their own work and identify the flaws in their own work. And you teach them that there will be flaws in their own work. And that's That's a really powerful tool. So when you teach data science in the context of real projects, you don't know the outcome. You can actually teach kids to challenge their own thinking and to challenge their own results. And we can teach them to think critically and analyze the information they're presented with. And we can teach them to demand higher standards of validation and reproducibility from others. So that if someone presents them with data and says, here is my evidence, they can say, well, what was the sample size? Why is there no 0 on the scale of that graph? Where is the rest of the data? How long did you collect it for? Can you compare it with some other situation? Trouble with this is it actually demands quite a lot of setup work. And the only reason I could do it when I was teaching is that I was half-time. So I was using my own time to find the data sets, to make sense of them. One of the first data sets I used was a voting data set from our federal election. You can actually download a CSV file, so a spreadsheet file, which has all of the votes in it. Obviously not with names attached because we don't know those, but every line in the CSV file is a single vote, so it shows exactly what happens on the ballot paper. And our Senate ballot paper is insane. It's the data set that I was using then had 151 boxes on that ballot paper, and there's above the line and below the line voting. It's really quite complicated. And the trouble with that data set was that I couldn't find anyone at our electoral authority who could explain to me how it worked. Because the ballot paper is two-dimensional, but the string that you get that represents the vote is a one-dimensional string. So how does the one dimension map onto the 2 dimensions? I couldn't find anyone to tell me. There must be someone, I assume, but I couldn't find them. So I had to figure it out from first principles and go, okay, well, the major parties will have got the most votes, and try to figure it out. And we got some really interesting results because the kids could then look at, well, what did the people in my community, how did they vote? And was that different from the people in the broader community? Was it different from the people in the country as a whole? They could ask a whole lot of different questions. Every kid asked a different question of that data set and then had to do a slightly different analysis and a slightly different visualization to answer the question. They weren't learning any different coding skills from the ones they were learning when they were doing pretty pictures in Scratch. They were learning functions and variables and selection and iteration, but they were doing it in the context of a project that had meaning and made sense to them. So we did projects on microbats, which are like bats that are about the size of your thumb. They're really, some people think they're ugly. I think they're super cute, but they're really interesting. And I had connections with a citizen science group that had 10 years of data on microbats from a couple of local parks. We did projects on climate science. We did projects, as I said, on election data. The interesting thing is it didn't seem to matter what the topic was. The fact that it was real and that the data set was real and messy and ugly made the kids a lot more engaged. So I used to get them coming to me when we were doing the pretty pictures in Scratch going, why are you making me do this? It's not relevant to me. I'm never going to use it. It's a waste of time. They cheated like heck. They weren't interested. When we started doing the same skills, but in the context of real data, that feedback went away entirely. And now I was getting them coming to me going, oh, I used this in my science project and I used it in my maths exam the other day. And oh man, there was a graph in the newspaper the other day and it was outrageous. They didn't have a 0 on the scale. So, they're actually starting to apply these skills to real life stuff, which is why I created my organization, the Australian Data Science Education Institute, so that I could find the data sets, make sense of them, hand them to teachers as ready to go lesson plans and projects and stuff to try to take the time out of the equation for teachers, but also so that we could train teachers to do this stuff and build their skills. A lot of the time we just use Excel or Google Sheets or whatever the teachers are using themselves in the classroom rather than programming. I'm a computer scientist by training. I would like everyone to program, but you got to build that up gradually. And I'm perfectly happy for people to be using real data sets, but using them in Excel if they're learning those critical thinking skills and getting meaningful results from it. So that's kind of a background. We've done a lot of projects with existing data sets, but some of my favorite projects are actually the ones where kids solve problems in their own communities, because you build this idea that what they're doing is they're learning STEM skills that they can use to make change. And suddenly now they have the motivation to do STEM skills, and it's not just playing with toys, and it's not just something that they have to do to get a tick mark on their report card. Suddenly it's something meaningful. So what's important to remember is that we tend to think of data science as way too hard for us. We think of it as really complex statistics and terms we don't understand, like k-means clustering and machine learning, and we think we have to have insane coding skills. We absolutely do not. You can do data science with a spreadsheet and the average function and sorting and graphing, really quite simple skills. The key thing is to be using real data. So the projects that we do, these local projects that I talk about where kids solve problems in their own communities, there are some really important steps there that we don't tend to see in the real world nearly enough. So first of all, the kids find a problem and they can identify the problem themselves, or you can give them one that's sort of relevant to the local community. They measure it, they analyze that and communicate those results. So that can be graphing for your really young kids. The graphing might be stacking blocks or developing some kind of tactile representation, and for the older kids they can be using Excel or using code. Then they try to fix the problem, and this is the step that I'm really passionate about. They measure it again to see if it worked. We tend not to do that in business and government and schools. We throw the latest greatest idea at something and then we walk away. We don't stop to go, how well did it work? Where did it not work? Who was disadvantaged by this wonderful new innovation that we brought in? Like the iPad point of sale systems, where you have to enter your PIN on a smooth screen, which I probably don't need to tell you, it's a bit of a challenge when you can't see the screen. Whose idea was that? Stop and go, this works great for some people. Who does it not work for? We're not even asking that question. So we teach the kids that you have to ask that question. And we've done projects like litter. Every school in the world that I know of has a litter problem in the yard. So they collect the litter, they analyze it by splitting it into types, and it might be litter from the canteen versus litter from home, or it might be paper, plastic, and metal. It doesn't matter. The kids choose the categories, and then they visualize that. And again, it might be stacking blocks or it might be code. And then they implement some kind of litter management program. So maybe they put bins somewhere differently if they found that all the litter was being dropped in the basketball courts or whatever. Or they might have campaign encouraging people not to bring litter to school and to bring their food in containers rather than in plastic wrap or whatever. And then they measure it again to see if it worked. And of course, there are problems with that, because if you collect litter on 2 different days, there are any number of ways that those measurements can't be compared, because maybe the grade 5s were out on excursion that day and they're the ones who drop a lot of the rubbish. Or maybe it was a windy day and half the rubbish blew away. So right from the get-go, they're having to ask the question, what is wrong with my data? What were the factors that were different in the 2 times that we did those measurements? How might that have affected it? How can we change this project so that we can account for those problems? So they're learning that it's not straightforward and there is no right answer, because that's the real world, right? I have yet to encounter a real world situation that has a textbook answer. So I was thinking, I had a chat to some folks with who are visually impaired or have visually impaired kids, and was thinking about some of the kinds of projects that might be relevant to them and they could get passionate about. And it was things like uneven footpaths and poorly placed signs and street furniture and tree branches at head height, or websites that are not accessible. So imagine that you do a project where you measure that in your local community. You pick a category of website that the kids have to interact with a lot and look at a bunch of different sites within that category, whether it's government sites or school sites or whatever, and you actually measure how many of the images have alt tags, how many ways does it muck up my screen reader, how many ways is this accessible and how many ways is it not? You actually measure it, and then you feed that back to the relevant authorities. So if you were doing uneven footpaths, maybe they even create a device that measures the footpaths. So, you have, attach some sensors to a broom or something and count all the times that it bumps over something that would be a problem for someone trying to navigate the world with a cane. And then you feed that back to the local government and say, you need to fix it. We can show you all, there are 15 just between the school and the local shop, or, whatever it is. So that what they're learning is they can do things that have a real impact and that can actually change the world for them and for their communities. And it can be as simple
we ever
as,
had in Boston was just like this.
sorry, what was that?
No muss, no fuss. Order your meal and move on.
I think it was just a muting accident.
Okay, I'll keep going. So, it can be really simple, or it can be as technical as a robot with an ultrasound sensor that maps the territory, or you can attach sensors to a cane, or, it doesn't matter. You take it from where the kids are up to and the skills you want to teach, and you build that into the project. And so the process then is you count or measure the problem. How many obstructions are there on the footpath? How big are they? It's the nature of tech, Tommy, don't worry about it. And you analyze the results by location or by severity or by type. The kids come up with the categories that they think are meaningful and relevant. And then they do that visualization step. And when I was working with 10th grade students, we did the visualization by hand because I was teaching them Python. I don't know how many of you have used Python, but the graphing in Python is pretty ugly and difficult to use. So we just, I can see some faces scrunching up. Yes, exactly like that. So we just did paper visualizations, and that was great because it meant they could do things a lot more creatively. So one of the projects we did was climate science, and I had a kid represent temperature changes using turtles, because turtles, the sex of a hatchling is determined by the temperature of the sand in which the egg was incubating. So she did this visualization that was like a bar chart with 10 turtles in every column, but she colored the turtles according to the sex, according to the predicted temperature over time. And so the boys were red and girls were green, and by 2035, only the tip of the nose of the 10th turtle was red. So she's showing that the turtles are going to die out, which is devastating and true, but it's really powerful visualization, much better than she could have done if she just graphed that with a standard computer graphing package. So it doesn't matter how you visualize it. It could be making 3D models with paper mache, or stacking blocks, or building tactile representations. The key is it's about communication. So how you visualize it depends on who you're hoping your audience will be, and also depends on making it more creative and more compelling, but making sure that it stays valid. So they measure, make sure that their representation is actually valid and accurate according to the data that they have. That's one of the risks of making it creative, is that you can get carried away and the data gets a bit lost. So the stages of the project then, that sort of basic, those data science essentials, you've got your collection of data, you've got your analysis of data, you've got your visualization, then the problem solving step, and depending on the solution, depending on the problem, you design and construct the solution. Where you're using big global data sets from online, you can't always implement a solution. Maybe the solution is actually communicating the issue to your community, or making a video or building a website or something that to communicate those results. It doesn't matter so much. But where you're doing a local problem, actually trying to solve it is really important. It's one of the issues I have with design thinking programs, because often the design thinking project gets as far as designing the solution, and then it stops. It's like, you're done, hooray! But I have never seen a solution that survived contact with the real world without modification and adaptation, and without half the time making life worse for some portion of the community. And that's a huge issue in our tech industry in particular. It's a much bigger issue than that, but the tech industry is the kind of easiest example of it. So imagine if we built that into the way we teach, that kids learn to actually sit down and evaluate their solution and figure out who's helped by it, who's harmed by it, how can we make it better. Those questions become integral to every project. They're the default. You always ask them. So I started doing this work in order to teach kids to program, really. But for me, that's become a tiny part of the issue. The idea that we're teaching them to solve real problems and develop critical thinking skills and to ask challenging questions. I think those are really important. And if they never learn a line of code, I'm fine with that. If they've learned to think critically, that's absolutely key. So there's a bunch of stuff on the slides on how to do that, which I'm going to skip over for now. But one of the really important questions about the data is, does the data mean what you think it means? And there was a great example that I saw on Twitter a while ago that really highlights that. And the example was someone posted, me, after the third bunch of bananas turned brown on the counter, when did you guys stop liking bananas? And her kid said, I like bananas fine, but when they turn brown, you make banana bread. And she tagged that with your daily reminder that questionnaire responses don't always mean what you think they mean. And that's a really important thing to remember with data, that data doesn't necessarily tell you what you think it does at first glance. And so you have to ask a lot of questions and you have to be critical. And questionnaire responses are kind of classically challenging in that way. So you always have to ask them, what are their weaknesses in this data? And when you ask a kid, what does this data tell you? They often give you qualitative answers. So with the election data set, when I said, what can we get out of this data? The kid said, well, it can tell you who's the best party. And I was like, I wish it could. I really do. But I don't think the party that gets the most votes is necessarily the best party. And then you have the whole conversation around what define best. And your definition of best is probably different to my definition of best. And you have that whole conversation. The data can tell you what, but it can't tell you why, and it can't tell you those qualitative questions. So that's really important. And to remember that all data is basically what I call proxy data. So the data is a proxy. The data you have is a proxy for the data that you want. And one of the data sets I work with Pawsey is a data from the West Australian Marine Science Institute, where they've monitored the whales passing by on the coast. And the data that they have is the whales that they saw breaching. The data that they want is how many whales are there in that water. It's not the same thing. Hopefully it's close enough that you can use it for some purposes, but it's really important to remember the data you have is not the data you want. And that's particularly true in education, because we tend to think that the exam result is how much the kid knows. And when we're being honest with ourselves, we know that's not true. We hope it's close and we work really hard to get it as close as we can, but it's not the same thing. It's how well they do on exams, and it's how good they were feeling on the day, and it's how good your exam was. I once wrote an exam question where to leave it blank was actually the correct answer. Didn't mean to. The question was, what's the output of this code? And the code was the definition of a function, and the function never ran. So the correct answer was, there is no output. But if you left the page blank, technically that was right. Like, how do you mark that? So, our exams are not perfect either. There's a lot of stuff in the slides about the fundamentals of data analysis and stuff, which I think stands on its own. And there's some resources in there. There's in particular, there's a resource I wrote for CSIRO, which is what questions can your data answer, which goes into that idea of qualitative versus quantitative and how you can actually zero in on what questions the data can answer. And it's really important that when the kids graph their results, what they graph is actually what they think they're graphing. So often they'll put a title on the graph, which is grandiose, and it's like, and here we are having solved the whole problem, whereas actually the graph only shows a tiny part of it. So, zeroing in on that. Does it say that? Is that actually in your data is really important. And you can do a lot of this stuff, as I said, with sorting and searching and context highlighting and graphing and finding the minimum maximum, really simple spreadsheet skills. You don't have to be coding. There are some sample projects on the ADSI website. There's a link to that in the slides. There's a great new website, which is at Pawsey, called Learn at Pawsey, where we're building up a repository of cool projects where the kids fill out surveys and enter their data analyze the data set back, and they've got all of the data that all of the schools have ever answered, and it's really cool. There's a sleep project up there at the moment, and we're building a trees and well-being and space data set at the moment, which is going to be amazing. There are a couple of podcasts that I have that are, I hope, worth listening to. One is if you have the book, there's a podcast which is just the book. So you don't actually have to buy the book. You can go listen to the podcast for free, and it's just me reading the book. Or you can go buy the book. That would be great. But there's also a podcast called Make Me Data Literate, which is relatively new, where I interview people who do cool things with data, and we talk about some of the ways you can make that data accessible. And I've got some really cool interviewees on that. In the slides, there's a bunch of ways you can get in touch with me. There's a Twitter handle and an email address. And there's also a Facebook group, which is for teachers using data science in the classroom. That's well worth joining, because people share resources and talk about ideas, and you can jump on there and go, oh, I was trying to do this project, but this problem cropped up, and someone will have had that problem before and will have a good solution for it. So it's a good resource. There's about 600 teachers in there, and it's worth checking out. We have some time for questions and conversation if you want to jump in.
Awesome. Thank you very much, Linda. It's fascinating. I didn't know a lot of what you were doing nowadays. So this has been really awesome for me, just personally, to kind of hear all the details, and all the stuff you're mentioning about the methods for kids and stuff is fascinating, because that's such an integral part of data science. It's not just about running a t-test. It's about like questioning what you're thinking about. So yeah, for anybody that'd like to, you can put questions on Slack. You can just unmute yourself if you prefer. You can toss something in Zoom if that's your bag. Feel free to. I have questions, but I'd prefer to let other people ask them if they'd like. So go for it.
While you're thinking, Stefik, if you want to add me to the Slack, then I can pitch into the conversation later as well. I'd be happy to do that. It may not be a prompt response because the time zones are a little bit unfriendly, but I will get to it. So if you want to add me, that'll be great. I can jump in.
I will add you right now. 1 second.
I just want to say thank you for the presentation, and I bought your book while you were talking. So
that's awesome. Thank you.
It's now in my phone, so I plan on reading it later.
Fabulous.
The using real data for things is actually a math class that I was teaching, where we were trying to get students who were a little lower level in math to maybe engage with it more by using that real data and using things around them. So I'd like to know I'm not crazy with thinking that would be useful.
The trouble is, there's a lot of people doing great work in this space, but it tends to be one teacher isolated in a school with no one else they can talk to, which is one of the reasons I'm really passionate about community building, and which I'm starting to do with the Facebook group, is connect with other people who are doing the same stuff, so you don't feel alone and you get that cross-pollination and inspiration. It's great to hear that you're already on the right track.
Especially in my school of 60 kids and 12 and a half teachers. So each teacher's kind of their own department.
I see there's a question in the chat about the links. All of the links to the resources that I mentioned are in the slides, but I can, if there's a particular thing that you can't find, just send me an email or pop it in the Facebook group or in the Slack, and I will grab it for you.
Other questions? So, okay, well, I have 100 questions, but I'll just ask one. So I know in the United States, at least, data science is kind of like new. I mean, it's not new. It's been around since forever. But what I mean is that like it hasn't traditionally been taught at the high school level, for sure. And even at the college level, it's kind of hit and miss. Like there's some statistics programs that basically just changed their name and scratched out statistics and wrote data science on the top, even though it's not really the same thing. But What are they doing in Australia? Is this like, are they trying to make it like a required course, or like, are they, what is happening in data science in Australia?
Not enough is the short answer. So we have some data science degrees. You know, you can get a master's in data science. I think there's undergrads in data science now. They mostly use textbook data sets. So you get people graduating out of those who meet a real data set for the first time and go, but it doesn't come out perfectly. And they're just like, yeah, it's not supposed to. They're like, what? I've never seen that before. Sure. But also in schools, they're building data into some of the subjects and the curriculum here and there in a very haphazard way, but it's still, you know, you can get through an entire science degree without doing a data subject. It's not core, it's not in any way compulsory, and often it's not perhaps not as well taught as you might like, again, you know, the textbook data sets and stuff. So when people think we're going to do a data science course, they tend to think we're going to teach the statistics, we're going to teach the, you know, the graphing, but they teach it in isolation, sort of separate from the actual context. So the maths curriculum here in the higher levels, and sort of, you know, 9th grade and 10th grade, they have here is a bar chart, and you use a bar chart for discrete data, and here is a linear graph, and you use a linear graph for continuous data. That's it. They don't go, what are you trying to say with your graph, and who are you trying to communicate to, and what is the point, and what is the data? And you know, sometimes it actually makes sense to use a line graph for discrete data. It depends on what you know. None of that conversation enters into it. It's the mechanics and the technicalities, and I think that misses the really important stuff. So, you know, I'm on a mission, like I said, trying to make myself redundant, but I don't think my job's in any immediate danger.
I think I saw Leslie's camera turned on. I suspect
Yes.
she has a question.
Well, I loved what you said about the using of real data, but what I see as a challenge is a lot of teachers will use the fun drawing the picture with Slack and using the little robot mouse, and that really gets the kids' attention. But then, how do you make that leap? What is a good middle step to get there?
Well, I think that's a really good question because it's hard to do that connection from, you know, we've taught a few of the skills and now we want to do something real from it, but the gulf can seem immense. And that's why the problem solving in your own community thing is really powerful, because you can do that incredibly low tech with just, you know, whatever skills you're up to, or you can do it super high tech depending on where the kids are up to and what you want to teach. So instead of going, okay, now we're going to learn this new skill, you go, okay, now we're going to solve a problem that matters to you because it's something you see, like, you know, might be access to the basketball courts. You know, in most schools, there seem to be 3 or 4 kids who monopolize the basketball courts and like own it, like the basketball mafia, and the other kids don't get a go. Okay, well, actually measure it. You know, time, record how many people use the basketball court and for how long, and now can we come up with a system where we can share it, and there's a, you know, a roster or whatever they come up with the solution themselves, and then they implement it and they keep doing the timing and the measuring and see if it actually works. That way they're immediately into it because they can see the point. They'd be like, oh, I might get more time in the basketball court, hey. But also you can then build whatever skills you're trying to teach into the problem solving and the analysis part of the project without having to, the engagement is built in. Does that make sense?
It does, and I really like the idea of this micro project, because you use data that they might find interesting, like sea turtles, but they're so disconnected from sea turtles that you still have that gap. But this is,
that's right.
You know, basketball, that's something tangible that's right there in front of them. Yeah, I like that.
Thank you. The local problems are the most powerful, I think. They just the motivation is built in, and motivation is like 95% of the battle.
Yeah.
Anybody else want to ask Linda a question? I know it's that we're probably standing in the way of her coffee, and that's good. But I think we still have a few minutes if anybody else has a question. I did have one more, if it's okay, if other people don't have one, and that is just you've got a lot of just like really what seem like amazing resources. Can people use them, or are they like under like complex legal agreements, or like what's the
Everything is Creative Commons attribution, non-commercial. So don't make money off it, and make sure you tell people where you got it from, and then adapt it, run with it, share it back. If you do adapt it and you have a new version of something I've got up there, or something entirely different, and you feel like sharing it, please share it back, and I'll put it on the website and share it in the Facebook group and what have you, and tell people it's there. It's all, the whole goal is, it's one of the reasons I made ADSI a charity rather than a commercial organization, was this has to be freely available. This is not going to be for the private schools that have all of the funding, and the school with no funding and kids who haven't even had breakfast get nothing. This has to be available to everybody. So yeah, please take it, run with it, adapt it as you see fit,
awesome,
and enjoy.
Okay, well, if everyone can just please thank Linda for her time. She was kind enough to the travel wasn't very long given our world, but I really do appreciate it a tremendous amount. This is a great talk. I appreciate it a lot. And your work has been inspiring to me for a long time, and I appreciate what you do. So thank you again for coming and talking to us today.
Such a pleasure.
Yes.
It was so great to be here.
Thank you so much.
Thank you.
Really cool.
Thank you.
All right. Okay, so why don't we all take as I cough my lung out. Oh, sorry, I'll stop the recording.